Welcome back to our pandemic studio. Let's keep going. What I want to talk about today is the uncertainty principle and one other concept, that of a de Broglie wavelength, which I think should be familiar to most of you from your general chemistry classes or some other class. But let us put it in the context of our overarching theme of chemistry and light and see how it ends up mattering. So let's start with that actually. Let me remind you that when we were talking about photons as particles of light, we commented on the fact that photons had momentum. And we said that the momentum of a photon, in fact, remember that momentum is a vector, but we're only going to be speaking about the magnitude of the momentum vector. So not its direction, but just the magnitude, the length of the vector. So we may say, put these vertical brackets to indicate the absolute value of the vector, or the same, analogously or identically, we might say the length of the vector, the magnitude. We said that for the photon, this thing looked like h bar k. I believe I said this was hk. That was a mistake. It should have been h bar k. H bar is Planck's constant divided by 2 pi. It happens so frequently that it's usually given a different symbol, h bar, but nevertheless it's very closely related to Planck's constant. K, if you remember, the wave vector was equal to 2 pi over the wavelength of light. And if we put all of this together, what we would find is that the momentum of a photon is equal to Planck's constant divided by the wavelength of the photon. Prince Louis de Broglie had in a stroke of genius, asked the following question. If particles of light have momentum that depends on their wavelength, and other particles can also have a momentum, do particles that are not light also have a momentum? Have a wavelength associated with them? And so what that came to be found is to be known as is the idea of the de Broglie wavelength. The de Broglie wavelength concept arises from the supposition that if you have a particle that's not light, any other particle, its momentum, let's call it, if this is the momentum of the particle, the absolute value of the momentum vector, or the length of the momentum vector, we may just write as P, is equal to Planck's constant also over the wavelength. So this was de Broglie's hypothesis. Suppose this was true, that particles that were not light, so not periodic oscillations of the electromagnetic field, would also have some kind of a wavelength associated with them if they had a momentum. Which is a little bit weird, of course, because when we think of normal particles like electrons, protons, nuclei, it's not clear what the wavelength has to do with, right? Wavelength of a photon, or a particle of light, makes a lot of sense. Photons are, in some sense, a disturbance of the electromagnetic field, is represented by wave-like behavior, and therefore there's a periodicity of the electric field going up and down. And if there's a periodicity or an oscillation, there's a distance in space between the repetition of the same electric field. So the wavelength concept makes sense. It makes a lot less sense for a non-photon particle, but nevertheless, de Broglie proposed this, and it ultimately ended up giving him a Nobel Prize. So I want to leave that where it is, and I want to go back to the concept of a photon. But for now, I just want to be on the same page that the de Broglie wavelength is something that we should be aware of. Of course, we've encountered it before, we've read about it before, but I just want to remind you of that fact. So, having said this, let's go back to the photon. Let us remind ourselves how we thought mathematically we might represent the photon. Remember what we struggled with, that a classical light wave repeats itself many times over, right? It goes from peak to trough, and that distance is represented by the wavelength, that periodicity distance. When we spoke about the photon, or the particle of light, we said that a photon, being a particle, should not be like a wave that extends through a very long region of space and repeats itself over and over. It should be something that is reasonably localized in space. Nevertheless, it should still have something related to a wavelength associated with it, because it is still a particle of light, a particle that is related to the classical analog of the electromagnetic field. We said that for the photon, we might plot its electric field magnitude, and if it's traveling in the positive x direction, we said that the electric field of the photon might look something like this. That would represent a particle that is reasonably localized in space, but nevertheless has some kind of a repetition akin to a wavelength. We talked about the fact that the distance in space over which the electric field was not zero should be thought of as the effective size of the photon. That is to say, where there is an electric field, that's where the photon is, and when the electric field goes to zero, the photon is not there. And so delta x was, roughly speaking, associated with the physical size of the photon. At this point, we come to the topic that we want to take up and spend the rest of our time today talking about, and that is the uncertainty principle. What is the uncertainty principle? Let's remind ourselves. The uncertainty principle, Heisenberg's uncertainty principle, says this. Uncertainty principle states that if you have some kind of a particle whose uncertainty in position is delta x, meaning that the particle is to be found somewhere in the region of space delta x, not exactly at some specific point, but somewhere in a region of space. If the particle has an uncertainty in its position delta x, uncertainty in position, it will also have an uncertainty in momentum. And the uncertainty principle says that the product of the uncertainty in position times the product of the uncertainty in momentum, and specifically let us note that it's the momentum along the x direction, is approximately speaking Planck's constant. We're not going to be overly accurate about this. Roughly speaking, the product of the uncertainty in position times the product of the uncertainty, or I'm sorry, the product of the uncertainty in position and the uncertainty in momentum is approximately h, which means that if this is very small, this must be very large, so that still the product equals h. Or if this is very large, this should be very small, and vice versa. Did I just say the same thing? I think you understand what I'm trying to say. So this is the uncertainty in the particle's momentum. Uncertainty in particles' momentum. This is kind of interesting. Let's go back to this idea of the photon. If we're saying the photon is a particle that is roughly localized in space, i.e. it does not extend over all of space. What we mean by extend is its electric field is somewhere in some region of space we call delta x. If the photon is to be found in some region of space delta x, this represents, roughly speaking, the uncertainty in its position. It is somewhere along delta x. But if it has an uncertainty in its position, that it's not exactly at the point x, but it's somewhere to be found in the region delta x, it will necessarily have an uncertainty in its momentum. And so for the photon, we should say delta x, the uncertainty in its position, what we refer to as its rough size or its coarse size, times delta px should be approximately equal to h. But what is delta px? Well, we know that for the photon, I erased it unfortunately, p, let's say px in this case, is h over lambda. That's what we showed. And so delta x times delta of h over lambda is approximately h. The uncertainty in the position times the uncertainty in the quantity h over lambda is approximately h. You might cancel h from both sides and show that delta x times delta 1 over the wavelength is approximately 1. So that if the photon is not at some specific position in space, but is to be found in some finite region of space delta x, it will necessarily have a finite uncertainty in its 1 over lambda, or therefore in its lambda. Can't have an uncertainty in 1 over lambda if you don't have an uncertainty in lambda, such that the product of the two is approximately 1. If this is large, this should be small. If this is small, this should be large. What does this mean then? If the photon is to be found in some region of space delta x, it does not have a well-defined wavelength. Its wavelength is uncertain by some amount delta lambda, or delta 1 over lambda. If you wish, you can relate this to the frequency of the photon. And so when we discussed the photon here and we said, look, if we want a particle that is approximately localized in space, unlike a never-ending electric field, or classical light wave electric field, if it's going to be approximately in some region delta x, it does not have a infinitely well-defined wavelength. You cannot say that the photon has this specific wavelength. In fact, what we're saying is the photon has an approximate wavelength whose value is uncertain. So it's not exactly a rigidly defined quantity. There is an uncertainty in its wavelength. And of course, if there's an uncertainty in its wavelength, there's an uncertainty in its frequency. And so a photon, being a localized particle, does not have an infinitely sharply defined wavelength. It is itself uncertain. We'll come back to this in a second. What about for other particles? Well, we talked about the fact that this should, or we didn't talk about it, but now we should mention that this should apply not just to photons, but any particles. If a particle has an uncertainty in position, it will necessarily have an uncertainty in its momentum. And the similar expression should be holding for delta y and delta z, with a corresponding what's called conjugate momentum in y and z directions. So the uncertainty in position x is related to the uncertainty in momentum in the x direction. The uncertainty in position x, in fact, has nothing to do with the uncertainty in momentum in the y direction. They only have to correspond to motion along that direction that is uncertain. And so it's delta px times delta x, that is approximately h. And so we've seen this, of course, before, but perhaps we have not seen it discussed as relating to the photon, and commenting on the fact that this means the photon represented by this mathematical function does not have a perfectly well-defined wavelength. It is in fact uncertain. And so the color of the photon, in a sense, is not infinitely defined. It is a little bit uncertain depending on how localized the photon is. The more localized the photon is in space, the more uncertain its wavelength. And if you try to localize a photon to a point, you would know nothing absolutely about its wavelength. It could be any possible color. The more the photon is delocalized in space, the less the uncertainty in its wavelength. And remember, if we think about this in terms of classical waves, the classical electromagnetic wave repeats actually, I shouldn't even say that. I'll get myself into trouble if I go down the line of thought, so let me quit while I'm ahead. Okay, so now with this in mind, I want to keep going, and I want to mention another uncertainty principle, which I think is usually less encountered than this specific form of the uncertainty principle. The second uncertainty principle that I want to comment on is what's called the time energy uncertainty principle. Here's what the time energy uncertainty principle says. Let's just call it time energy uncertainty principle. What the time energy uncertainty principle says is that if you have a particle that existed for a certain amount of time delta t, its energy will also be uncertain. The uncertainty will be delta E, and the product of the two is approximately Planck's constant. By the way, as a sanity check, remember that Planck's constant is this fundamental quantum mechanical unit of action that we defined previously. The unit of action was, if I remember the definition, was related to a quantity that looked like momentum times distance. And so the units of this make sense. If this is action, the units on the left should be distance times momentum. And that's exactly what we find. But we also see that the unit of action is related to energy and time just as well. So this is kind of a weird one, and I want to talk about some manifestation that would be relevant for us as chemists studying the behavior of light and how it interacts with atoms and molecules. Let me once again say that if a particle has been in existence, or if something has existed for a certain amount of time, delta t, its energy will not be infinitely defined. It will also be uncertain by delta E. So if the uncertainty in the time is delta t, the uncertainty in the energy is delta E. If this is very large, this is very small. So if something has existed for a very long time, or has lived for a very long time, and we'll see what I mean by this in a second, it will have a very relatively certain energy. The uncertainty will be relatively small because the product always has to be equal to Planck's constant. But if something has lived for a relatively short time, it will have a very large uncertainty in energy, such that the product is approximately H. Where is this relevant? Let's imagine the hydrogen atom that we talked about last time. This is energy. Let's draw the first two energy levels with quantum numbers n equals 1 and n equals 2. So suppose a hydrogen atom is hanging out. All of a sudden it's bombarded by light, and the electron in the hydrogen atom absorbs light and goes from n equals 1 to n equals 2. So the electron in the atom, in the hydrogen atom, absorbed a packet of light, a quantum of light, such that the energy of that photon was equal to the energy difference between n1 and n2. And one thing we didn't talk about is what happens after some time after that. So the photon has been absorbed by the atom. The electron has been excited from n equals 1 to n equals 2, and then we wait. And we wait and we wait, and eventually after some time, it is very likely that the atom, the electron, will return back to its ground state, and in so doing, emit a photon. That's called light emission, also called fluorescence. And so excited atoms or excited molecules eventually, for the most part, emit that light back out. So they exist in the excited state for some amount of time. That time is called the excited state lifetime. And the excited state lifetime depends on what the atom is, what the molecule is, and so on. And so it's a very chemically specific quantity that reflects the specific kind of moiety, the specific species that you're thinking about or dealing with. But nevertheless, eventually this energy will come back out as light, and the atom will emit it back out. The fact that the atom was in the excited state for a certain amount of time that wasn't infinite, some finite amount of time. For example, normal molecules stay in their excited state for 1 nanosecond, 10 to the minus 9 seconds. And so the excited excitation, the excited state, the excited electron will stay excited for a relatively short amount of time, after which it will emit that light back out. Well, if it was in the excited state for a short amount of time, the energy of the photon that comes out, h nu, and therefore the frequency nu, will be uncertain. And so it's not always going to come out with the exact same energy. Sometimes the energy of the photon will be a little bit smaller, and sometimes it will be a little bit larger. And there will be an uncertainty in the precise photon energy that is emitted by the atom. And because the energy of the photon is related to its frequency, there will be an uncertainty in the frequency of the light that comes out, or the color, if you wish. And so we may say that the emitted light, or emitted photon, will have an energy somewhere approximately between E minus delta E and E plus delta E, roughly speaking. Really, we should put minus delta E over 2 plus delta E over 2 so that the full uncertainty is delta E. We're not going to worry about that right now. So if this excited state existed for an infinite amount of time, very, very long, the energy of the photon that would come out would be equal to h nu, and that would be exactly equal to this energy between energy level n equals 1 and energy level n equals 2. But because the excited state exists for a finite amount of time, that is relatively short, the precise energy of the photon will not always be this. It'll be somewhere in this range, E minus delta E and E plus delta E. What is this delta E? What is the uncertainty? It's this. And so if this is, in this case, the excited state lifetime, the time that the electron spends in the excited state, the energy of the photon that comes out is not going to be fixed. It's going to be uncertain by a quantity delta E such that the product is approximately equal to Planck's constant. That's interesting. It says that the color of the light that comes out is not always going to be the same wavelength, even though we're talking about the kind of a fixed set of energy levels. This, and so let's actually take this further. So for the photon, so if we have delta T, delta E, but delta E is delta H nu, right? If the energy is H nu, the uncertainty is the energy, and the energy can also be written as delta H nu approximately H, or delta T, delta nu is approximately 1. So that the shorter the excited state lifetime, the larger the uncertainty in the frequency of the light that comes out, the light that is emitted or fluoresced. The longer the excited state lifetime, the smaller the uncertainty in the frequency. If the excited state lifetime were infinite, the uncertainty in the frequency would be 0, and so the frequency of light would always be the same single number. But because the excited state lifetime is not 0, in fact relatively small, there will be some reasonable uncertainty in delta nu. This has interesting implications for the emission spectrum. Remember we talked about the idea of the absorption spectrum, the set of frequencies of light that an atom could absorb. There is an analog to that called the emission spectrum, the frequencies of light that the atom emits after it's been excited to an excited state. And so suppose we have a frequency axis, and somewhere here, call it nu naught, is the frequency of light that corresponds to this energy. The emission spectrum, if this is on the y-axis, let's plot intensity. So we're plotting the intensity of emitted light. Let's write that down. Intensity of emitted light when the electron comes back down to the ground state, and by energy conservation gets that energy out, and that comes out in the form of a photon. If the uncertainty in the frequency was 0, you would have a sharp line here that would say the frequency of the light that is emitted is nu naught, and here is its intensity. And there's no light emitted immediately higher at higher frequencies and immediately lower frequencies. But because the excited state lifetime is not 0, what you find is that the peak is broadened with a width delta nu, which represents the uncertainty determined by the excited state lifetime, and the product having to be approximately 1. This is actually really interesting because what it says is that if I measure the emission spectrum and I look to see how broad the spectrum is, what is the uncertainty in the frequencies of light that come out, right? What this means is that the frequency of the photon could be here, could be here, could be here, could be here, somewhere within this band. And then the frequency range, or the uncertainty, is what's usually called the full width at half maximum. This is approximately half the maximum. The width here is what's called the full width at half maximum. This delta nu should be thought of as the uncertainty in the frequency of the light. And this width will be larger if the excited state lifetime is small, and will be smaller if the excited state lifetime is large. And what's really interesting is that by measuring this width, you could measure the excited state lifetime. This broadening of the emission spectrum is called lifetime broadening. Broadening because the excited state lifetime is not infinitely long, but some finite point. And in fact, for certain excited states of atoms, this is exactly how their lifetime is, or the excited state lifetime is determined. You measure the emission spectrum, you look very carefully for the width of that peak, and you relate that back to the excited state lifetime. Now, in full disclosure, we must mention that the lifetime broadening, the broadening of the line because of the finite lifetime, the excited state lifetime, is not the only mechanism by which that line could be broadened. It could be broadened by a difference in environments in which atoms find themselves, because of thermal motions and other instrumental effects, where the instrument is not infinitely precise. But nevertheless, if everything was eliminated, if all the other sources of broadening were eliminated, the width of this emission line would be exactly relatable to the excited state lifetime, which is kind of cool. You can then go around from element to element and ask, what's your excited state lifetime? What's your excited state lifetime? And then you might be able to learn something interesting about that atom, or about the way that atom interacts with light, from that consideration. So that's all I wanted to say for the uncertainty principle.